Hi, today's lecture will be on the rumor spreading on the complete graph. Having gone through preliminaries on Markov chains and the Poisson process, we are now ready to start with the main topics of this course, which is stochastic processes on networks. And the first such process that we are going to look at is rumor spreading. But before we start on that, there are some more preliminaries we need to go through. So I will introduce some terminology about graphs and networks before introducing the problem we are going to look at today. Okay, so throughout this course, I will use the terms network and graph interchangeably. So a graph or network, denoted G, consists of a vertex set V and an edge set E. So V is a set of elements called vertices. An edge is a pair of vertices. So it's a subset of the Cartesian product of the vertex set with itself. And an edge might be, so the order here might or might not matter. So an edge is called undirected if the order of vertices doesn't matter, meaning that UV and VU refer to the same edge where U and V are vertices. But if these refer to distinct edges, then these are directed. Okay, and a graph is called directed or undirected if all its edges are of the corresponding type. We're missing T there. The graphs we study in this course will all or mostly all be finite, meaning there will be only finitely many vertices and hence only finitely many edges in the graph. So now I'm going to introduce some terminology which most of you may already be familiar with. So the first thing we are going to define is a path. A path is a sequence of vertices such that for every two vertices in the sequence, so for each I and I plus 1, either both Vi and either there is an edge from Vi to Vi plus 1 or Vi plus 1 to Vi. So if the graph is undirected, there is no distinction here. If the graph is directed, then what we are saying is that we call something a path if there's an edge between every pair of successive vertices, but we are not necessarily keeping track of the direction. Okay, so let's be a bit more concrete. So you could think of, let's think of a concrete example of a network. So let's look at a road network in a city. So the vertices are junctions and the edges are roads between junctions. And the roads may be one-way or two-way. If they are one-way, the edge is directed. If they are two-way, the edge is undirected. And a path then is a sequence of roads connecting two intersections where we don't care about the direction. So if we can get from A to B, ignoring whether roads are one way, then there's a path between them. That's the definition of a path. Okay. Okay, and if in addition, the last vertex is the same as the first vertex, we call it a cycle. Okay, a couple of qualifications. So here I've used the term path only if the vertices are distinct, so there are no loops. So if I get from U to V, circle around V, and go from V to W, that's not a path. I think in the notes I've called that a path, but not a simple path. But okay, there's some variation in the terminology here. I'm going to use path now for sequences of distinct vertices with an edge between every successive pair of them. And if the last and first vertex are the same, we call it a cycle. The one thing we don't call a cycle is a two-edge path. So if I go from V1 to V2 and come back from V2 to V1, I don't call that a cycle. So a cycle must have at least three distinct edges along it. Okay. And again, we don't allow vertices to be repeated in our definition of a cycle. So that's a path and a cycle. We'll call a graph connected if for every pair of distinct vertices, there's a path between them. And again, let me remind you, we don't care about the direction of the edges to say that there's a path between them. So a graph is connected if you can get from anywhere to anywhere else, possibly going along edges in the wrong direction. A graph is called complete if every pair of edges is present. So for every pair of vertices, there's an edge between them. And we'll denote the complete graph on n nodes by k sub n. A complete subgraph of a given graph is called a clique. So a clique is a collection of vertices within a graph where for every pair of vertices, there's an edge between them. The name is revealing. So if you think of your graph as a social network, the vertices as individuals and an edge between two vertices as denoting that they know each other, then a clique is a group of individuals who all know each other. Okay. An undirected graph is called a tree if it is connected and acyclic, so if it has no cycles. So for every pair of vertices in a tree, there's a path between them, but there are no cycles, and it's easy to see from this that there is therefore a unique path between them. Okay, okay, so that's all the terminology about graphs we need for now. If we need more terminology later, we'll introduce it as we go along. You might want to draw these things just to make sure your intuition about these objects is clear. Okay, so now we are ready to introduce our model for rumor spreading on the complete graph. Let me introduce the model first and then motivate it a bit. So we have a population of n nodes. You can think of them as individuals, and any pair of them can communicate directly. So there's an edge between every pair of nodes, meaning that that's what it means for the graph to be complete. So any pair of nodes can communicate directly. Initially, a single one of these nodes or agents knows a rumor. And then everybody who learns this rumor is going to spread it. And we need a precise mathematical model of how the spread happens, the times at which it happens, who they choose to repeat the rumor to, and so on. And so we'll specify that model. So first, we'll specify the times at which a node chooses to communicate the rumor. To do that, we are going to associate a Poisson process with every vertex. The vertices are the individuals, represent individuals. By the way, I'll also use the term node and vertex interchangeably. They mean the same thing. So at each node V, there's a Poisson process, which we denote by n sub V. We are going to take the rate of this Poisson process to be 1. So that's what unit rate means here. The rate or intensity of this process is 1. So recall that this is a counting process. It starts at 0 and it After a random time, it goes up to 1. After another random time, it goes up to 2, and so on. And these jump times, the times at which at which the counts increase by 1, these are called the increment times. And these will denote the times at which the node chooses to spread the rumor. Okay, so every time, so think of the Poisson process at a node as an alarm clock at that node. And this alarm clock rings not after fixed times, but after random times, random exponentially distributed times. And every time this alarm clock rings, the corresponding node decides to spread the rumor. Okay. Okay, so, and how does it do so? So when the alarm clock at vertex V rings, it wakes up and it chooses a node W uniformly at random from the vertex set. There's no preference. You are not more likely to spread the rumor to some friends than to others. You choose who to spread it to at random. Okay, and then you communicate the rumor to W if you know the rumor at that time. Just for convenience, I'm going to allow for the possibility of spreading the rumor to yourself. Nothing, this is not important. This is just for notational convenience. Okay, so that's the model. Take a moment to make sure you understand the model. So every vertex has its own independent alarm clock, which rings at the points of a Poisson process. I'm sitting at one of these vertices. When this alarm clock rings, I wake up. If I haven't yet heard the rumor, I do nothing. I have nothing to communicate. If I know the rumor already, then I decide to communicate. And how do I do that? I pick someone uniformly at random, completely independent of the past. So I don't keep track of who I have already passed on the rumor to. I just uniformly pick someone, maybe the same person I picked last time, and repeat the rumor to them. And I could also repeat it to myself. So that's the model. Okay, and I hope that's completely clear. Okay, I already said this. These processes are assumed to be independent. Okay, what are we interested in? So what happens in the long run? Nobody forgets the rumor, so the population is finite, so eventually everybody learns the rumor. That's what happens. So the only interesting question here, the main interesting question here is, how long does it take until all n nodes know the rumor? Typically, we are going to be interested in what happens in large systems. So we want to let n go to infinity, and we want to ask, how does the time for the rumor to spread scale with n? So if you have a million times a million people, does it take, as opposed to, let's say, 1,000 people, does it take 1,000 times as long for the rumor to reach all of them? So does it scale linearly with n? Or does it scale slower? Maybe does it scale like square root of n or some other function of n? So that's the kind of question we want to try and answer. Okay, and we care about what happens for large n. So I might be a little bit sloppy with some of the calculations. I don't care about the difference between n and n minus 1 or n and n minus 20. But I do care about the difference between 2 times n and 3 times n, and so on. Okay. Okay, a bit about motivation. Okay, so this is a somewhat okay, you might feel that this is not a very serious question to look at, but it does have relevance to practical questions. For instance, economists are interested in how information spreads in social networks, information about things like um, job market openings, or how different technologies get adopted in a system, or different practices get uh, adopted in organizations. So how does information spread in societies or organizations? So that's one question that is of interest to economists and social scientists. But it's not only in human beings that information spread happens. It happens in animals, in social insects, for instance. Um, so when bees or ants decide to forage for food, they have scouts who go around searching for food. They come back to the nest and signal information about the food source to the nest. And the question is, does every individual in the nest, are they able to receive the signal directly, or is it mediated through other members within the nest? So does it spread more like a rumor, and then does the whole group decide which of these different food sources to go and forage? So that's so biologists are interested in the question. And in fact, this happens even in not only in insects, but in extremely simple organisms and bacteria. So um, when so you have these bioluminescent bacteria in the oceans, and when the concentration of them is large enough in some part of the ocean, then the population as a whole decides to glow. It's not that the individuals by themselves, when they are not in big groups, don't glow, but when they get together in these large groups, they all decide to bioluminesce together. And how do they do this? So this is called quorum sensing. They somehow are able to sense that the number or concentration of bacteria around them is large enough and decide to glow. So biologists are interested in these quorum sensing mechanisms. So these are all examples of rumor spreading. And it's also important in algorithms and computer science as a way of spreading information around large systems like replicated databases, or for distributed computation or sensor networks and so on. Okay, so there is a lot of relevance to real world questions of this extremely simple model. Okay, you might at this point be thinking that there's an even simpler way of modeling this, and this is somewhat complicated. So here is the simpler way of modeling it, which is in discrete time. So you have a population of size n. Again, a single individual knows a rumor. Time is discrete. In the first time step, this individual passes on the rumor to someone chosen at random. In the next time step, two of them know the rumor. Each randomly picks someone to tell the rumor to. They may pick the same person, in which case one of the communications is wasted, or they may pick different people, and this continues forever, that everybody who knows the rumor randomly chooses who to tell it to in the next round. And we could analyze that process as well. So given that much simpler way of describing a closely related model, why have I chosen this more complicated description? It turns out that the analysis is much, much simpler for this model than for the discrete time model. So that's why I have chosen this. Some of you might wish to study the discrete time model. I'll talk about that later on. But we are going to analyze this continuous time version because it's much easier. Okay, so I'll pause again. If you like, go over this once more, make absolutely sure you understand the model fully. This is a complete description of how the rumor spreads. And given this description, it should be possible to answer this question about characterizing the random variable t sub n, the time for n nodes to learn the rumor. Okay, and that's what we are going to turn our attention to now. Okay, it turns out that it's easier to analyze the model using an equivalent description where instead of putting the clocks on the vertices, we put the clocks on the edges of this complete graph. And there is an equivalent description of the model in this way, and that's what we are going to construct now. So here is my claim that the node-based rumor spreading model is equivalent to the following edge-based one. Recall that in the node-based model, there are independent Poisson processes, one at each vertex, and the rate of each such Poisson process is 1. Now, the Poisson processes are going to sit on the directed edges VW rather than on the vertices, but their rates are going to be 1 over n. And these are all going to be independent, okay? So now, instead of an alarm clock at each vertex, there's an alarm clock on each directed edge, and these alarm clocks ring after independent exponential times of rate 1 over n and hence of mean n. Okay, so that's recall the equivalent descriptions of a Poisson process. So the increment between counts of the Poisson process are exponential random variables with parameter equal to the intensity or rate of the Poisson process. Okay. So now what's the description of rumor spreading in this model? So whenever the alarm clock on the edge VW rings, then if V knows the rumor at this time, then the rumor passes to W. If V doesn't know the rumor, nothing happens. If W already knows the rumor, well, it hears the rumor again, but its state doesn't change. But this is the description. So whenever these alarm clocks ring, the rumor passes along the edge. Okay, so this is another model for rumor spreading, and my claim is that this model is exactly the same as the node-based model. And why is that? Why are these models exactly the same? To see that, let's go back to the vertex-based model and see when V tries to spread the rumor to W. Two things need to happen for that. So firstly, the alarm clock at V needs to ring. Then V wakes up, and then it picks a node uniformly at random, and it has to choose W. So if V wakes up and chooses W, then it spreads the rumor to W. So what are the times at which V contacts W? It's obtained by taking the Poisson process of times at which V contacts somebody and splitting them with probability 1 over n to say these are the times at which W is chosen. So this is a Bernoulli splitting of the Poisson process n sub V sitting at vertex V, right? So we take the Poisson process at V and we split it to say which vertex it's going to communicate to by tossing a coin with probability 1 over n for choosing that vertex. And so we are using the result that says that Bernoulli splittings of Poisson processes give us independent Poisson processes. And that's why the processes of times at which V contacts W are Poisson processes of rate 1 over n. Okay, so that shows the equivalence of the two models. Again, it's worth taking some time to make sure you're convinced of this equivalence. Okay, now we are going to use this edge-based description to analyze the Rumour spreading time. Okay, so let's define by T sub k the first time at which at least k nodes know the Rumour. By the way, inf here means the same as minimum. This is infimum, and it's just another word for minimum. There's a very small and subtle difference. If you have not come across the term infimum before, just read minimum wherever I've written infimum. So Tk is the earliest time at which at least k nodes know the Rumour. So we started with a single node knowing the Rumour, so T1 is 0 by definition. And we are interested in the first time that all n nodes know the Rumour, which is exactly what we called Tn earlier. Okay, so what can we say about the time Tk between Tk plus 1 and Tk? So how much longer, if we start with k nodes knowing the Rumour, how much longer does it take until one more node learns the Rumour? So this is what we are going to look at. And this is where our assumption about building the whole description on Poisson processes comes in. And we are going to very strongly use the memoryless property of the Poisson process. So various things have happened up to time Tk to ensure that k nodes have learned the Rumour. But we don't need to know what happened because of the memoryless property of this process. The future evolution doesn't depend on the history up to the time Tk, on how the Rumour spread until time Tk. All that we care about is that there are these k nodes here which know the Rumour. Okay, so at time Tk, there are k nodes which know the Rumour and n minus k nodes which do not. Do we care which particular k nodes know the Rumour? Should we? Okay, again, from the symmetry in the problem description, I hope you'll be willing to believe that we don't care, that it doesn't matter which nodes know the Rumour, it only matters how many of them there are. Okay. Because they all behave identically with each other. So we don't have to keep track of which ones learned the Rumour, and that greatly simplifies the description as well. Okay, so at time Tk, there are these k nodes here which know the Rumour, and n minus k nodes here which do not. Now, what can happen? So there are two nodes within this set which could communicate, in which case a node which knows the Rumour repeats it to somebody who already knows the Rumour, so nothing happens. Or two nodes within this set of size n minus k could talk to each other, in which case, since neither of them knows the Rumour, again, nothing happens. The only thing that matters is if some node in this informed set here chooses to speak to some node in the uninformed set, right? Those are the only types of communications which pass the Rumour to a node which doesn't already know it. So what we are interested in is the rate at which these communications happen. Well, to calculate that, we need to know how many edges there are from these informed vertices to these uninformed vertices. Now, this is the complete graph, so there's an edge between every pair of vertices. So there are k vertices here and n minus k in this set. So there are k times n minus k edges going from informed vertices to uninformed ones, right? It's just counting. And so it's only communications on these edges that matter. Okay, so what about, so let's pick one such edge. When do communications on that edge happen? They happen according to a Poisson process of rate 1 over n. We saw that already. That's per edge, and then there are k times n minus k edges. So what's the total process of communications happening on all these edges going from this set to that set? It's the superposition of all these k times n minus k Poisson processes. So we are superposing this many Poisson processes, and they are all independent as well because Bernoulli splittings are independent, etc., etc. So we are taking this many independent Poisson processes of rate 1 over n and superposing them. So the aggregate is a Poisson process of rate, which is 1 over n added with itself this many times. So of total rate k times n minus k over n, right? So that's the aggregate process of times at which this set communicates with that set. And as soon as the first set such communication happens, one more vertex learns the Rumour. Okay, so tk plus 1 minus tk is the time until the first increment of this aggregate Poisson process. The Poisson process has this rate. The times between increments are exponential with this parameter. So the time until one more vertex learns the Rumour is exponential with this parameter k times n minus k over n. Okay, so this tilde symbol here just means that this random variable has this distribution, is distributed like this. Okay, again, it's worth pausing to make sure you understand this. This is the core of the analysis, to say how long does it take for one more node to learn the Rumour when k nodes know the Rumour. Okay, so now let's put things together. So let's write Tn, this is the object we are interested in, as a telescoping sum. So I can write Tn as T1 plus T2 minus T1 plus T3 minus T2, and so on all the way to Tn minus Tn minus 1. That's what I've done. We have T1 is 0. We started with one node knowing the Rumour, so we can drop this first term. And now I'm going to take expectations on both sides. So the expectation of Tn is the expectation of this sum. But let's now look at just one term here. So what's the expectation of Tk plus 1 minus Tk? So we saw that this time difference is an exponential with this parameter. And let me remind you that an exponential with parameter lambda has mean 1 over lambda. So the expectation of this random variable here is 1 over this. So the expectation of tk plus 1 minus tk is n over k times n minus k. And if I expand this in partial fractions, I get this here. Okay. And now we can plug this in here. So what can we say about the expectation of Tn? T1 is 0, so the expectation of Tn is the expectation of the sum. And now by linearity of expectation, the expectation of a sum of random variables is always the sum of their expectations. No independence is required. This is always true. So the expectation of Tn is the sum from 1 to n minus 1 of these expectations, and substituting this here, I get the sum from 1 to n of 1 over k plus 1 over n minus k. And if you look at this series, these two series are exactly the same. So when we are summing 1 over n, we are counting from k equals 1 to n. When we are summing 1 over n minus k, we are counting down from n to 1, or this should be up to n minus 1, not up to n. Sorry, there's a typo there. But these two sums are the same, so we get 2 times the sum. Okay, and now the sum from 1 to n of 1 over k, this is called the harmonic series. You might know already that the sum of the first 10 terms in the harmonic series is approximately log n. You can also show this is the case by approximating the sum by an integral that's in the lecture notes. I won't go through this again. You can check the lecture notes for that. So this sum is approximately log n, and it's a bit more precise than that. When talking about random variables, I use this tilde notation to mean equality in distribution. I'm using the same notation here to mean something else. So do pay attention to the context. So here I'm using this to mean asymptotic equivalence. And what do I mean by that? So we say that two sequences AN and BN are asymptotically equivalent if their ratio tends to 1 as n tends to infinity. Okay, and it's just a property of the harmonic series that it's asymptotic to the logarithm function. One more remark, we will use logarithms throughout this course, and whenever I use this terminology, I always mean natural logarithm. If I don't write the base of the logarithm, the base is e. If I want any other base, I will denote it here. Okay. All logarithms are natural unless otherwise specified. Okay, so that gives us the mean Rumour spreading time. So that was that was the main point I wanted to make in this analysis. So so to summarize what we have done so far, we introduced a Rumour spreading model on the complete graph. The model was in continuous time and it was built on Poisson processes. Everything happened according to independent Poisson processes. And we analyzed the time it takes to spread the Rumour to everyone in the population, starting from a single individual. And we showed that the mean time for everybody to learn the Rumour scales like 2 log n. I want to just make one point about this here. You can see that the Rumour spreading time grows very slowly in the population size. It grows only logarithmically in the population size. And intuitively, that's saying that Rumour spread very quickly. So that's a qualitative insight into Rumour spreading that I think is useful. Okay, so next time we are going to do a slightly more detailed analysis of this. So we've only looked at the mean of this random variable in this lecture. Next time we'll try to say a bit more about the distribution. Not a lot more. We are going to calculate the variance, and then we are going to use that to prove a limit theorem for the sequence of random variables t sub n indexed by n. But I'm going to stop this lecture here.